Good morning, everyone. So we spent the last couple days developing and using some derivative rules. So now we're going to go through proofs of some of the rules. Okay, so this will give an idea of the general structure of how you would prove that one of these rules is true. Okay. So we're going to start with the simplest one, which is the derivative of a constant is equal to 0. Okay, so to run through these proofs, we're going to go back to the first principles definition of the derivative. So, proof. So, the derivative of a constant is equal to, okay, so again, any kind of a derivative in the limit as h goes to 0 of f of x plus h minus f of x over h. Okay. So what we would do here, right, is we plug in x plus h and x into our function. But our function is just a constant. So when I do that, I get the limit as h goes to 0 of c, take away c over h. Okay. So that would be the limit as h goes to 0 of 0 for h. Okay, well, 0 divided by anything, okay, remember we're approaching 0, not necessarily at 0. Okay, so h divided by some, 0 divided by some number is just 0. Limit as h goes to 0 of 0. Okay, but h is gone now, so that's just 0. Okay, and we are proven. Okay, to sign off on your proof, there's a few different ways you can do it. Okay, I like to do this little, you just draw a little shaded square. Okay, you can write QED if you want, okay, whichever you would like. So that was a nice simple one. Let's rev up to something more complicated. So now we're going to prove okay, the power rule. Okay, when you have the derivative of power, you just bring down the exponent and you reduce it by 1. Okay. We're going to go through two different proofs of this because there's a couple different ways you can do it. Okay. So the first one, okay, this is going to look a little different than what we've done before. Okay, so here's some things we need. So two rules. Proof. Okay, so the first one, and we mentioned this a while ago when we were talking briefly about difference of cubes. Okay, if I have a difference of any kind of powers, okay, one of those factors is x minus a. Okay, and what I get as my other factor is just a sequence of descending and ascending powers. So this would be x to the n minus 1 plus x to the n minus 2 e to the power of 1. Okay, and so on. Okay, up to x a to the n minus 2 plus a to the n minus 1. Okay, so the powers of x would start at 1 less and count down. The powers of a would start at 0 and count up. Okay, so that's the first one we're going to make use of. Okay, the second one, okay, is another way I can write the expression for a derivative. Okay, so this is another way you can do it. We haven't really seen it before, okay, but I think you get the idea of how this would work. Okay, so the derivative of a function is the limit as x goes to a of f of x f of x minus f of a over x minus a. Okay, so in this expression, right, the difference, the way I'm closing the gap is that the value of x, the first term, gets closer and closer and closer to the value of a, second term. So I'm approaching, right, a minus a and f of a minus f of a. Okay. So now that we have those two things established, okay, we're ready to actually begin the proof. So we're going to start this off just like the constant one, right? The derivative of x to the n is equal to, I'm going to use my other expression here, so the limit as x goes to a of f of x minus f of a over x minus a. Now I just do my substitution. Okay, so in the numerator, I'm going to have f of x will be x to the n, and f of a to the n, x minus a. Okay, now I'm going to make use of that other rule we just introduced. So this is going to expand a bit here. Okay, so in my numerator, I can factor that into x minus a times x to the n minus 1 plus x to the n minus 2 times a plus and so on plus x to the n minus 2 Okay, the whole thing was divided by x minus a. Okay, so much like with the whole, when you approach, h approaches 0, we're trying to cancel out h. Okay, you can see that we're going to be able to cancel out a now. Right? I can divide both sides, sorry, top and bottom by x minus a. So I get the limit as x approaches a of just that second part on the top, x to the n minus 1 plus x to the n minus 2 times a plus, okay, this time I'm going to write the third one in just to show what's going on. So next would be x to the n minus 3 a squared, and so on up to a n minus 2 and a n minus 1. So now I can substitute, right, I've gotten rid of my problem, right? I don't have a minus a on the denominator anymore. So I can substitute. So as x approaches a, I want to substitute a wherever I see an x. So this expression becomes a n minus 1 plus a n minus 2 times a plus a n minus 3 times a squared plus, and so on, a minus 2 a to the n minus 1. Okay, so let's start simplifying those exponents. N minus 1. Okay, I have a to the n minus 2 times, well, really a to the 1. So I add those exponents together. I have n minus 2 plus 1. So I'm back to n minus 1. The next one, I have n minus 3 and then plus 2. Like this one right here. Well, that's also going to give me n minus 1. Okay, so if I keep going all the way through here, a n minus 1. Okay, so I have a whole bunch of a to the n minus 1s. How many of these do I actually have? So if you think back to the difference of cubes, right, the pattern was we had our factor and we ended up with 3 terms, right, squared, 2 powers of 1. Okay, so if you count out how many a's are here, okay, there are actually n of those. So this is n a to the n minus 1. Okay. Okay, so I know I kind of have the wrong variable there. Okay, but it's essentially showing me, right, for any value of a that I approach, I end up with this expression, right? So therefore, okay, it doesn't matter what value I have to substitute in x to the n. I'm going to get something that looks like nx minus 1. Okay, so proven. That's what I wanted to show, is that I got down to that kind of expression. Okay, that's version 1. here comes version 2. And this, for this one, we're pulling in a different tool. Okay, so for version 2 of this proof, we're going to use what's called the binomial theorem. Okay, for those of you who took data last semester, you've seen this thing before. Okay. The choose terms, okay, this whole n over 0, okay, that's what's called a choose term. Okay, it really relates to Pascal's triangle. So you might remember in grade 11, you would take this shortcut to expand things out where you'd write down numbers from Pascal's triangle. Okay, that's basically what those numbers are. These expressions here, this is n choose 0, n choose 1, n choose 2, and so on. Okay, so if you're not, talk to somebody who took data, they'll be able to fill you in a little bit about what it is. Okay, but underneath there's the expression with factorials for what that is. Okay. So we need to make use of this in order to use what we're going to call the normal expression for derivative. So here we go, round 2. I'm going to start off with our expression. So the derivative of x to the n is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so now I'm going to do my substitution. This is the limit as h approaches 0 of, I'm going to have x plus h to the n minus x to the n. And that's all over h. Okay. So again, we're doing this before. Our goal will be to expand that out and try to cancel out h. So that's why we have to bring in the binomial theorem now. So this equals the limit as h goes to 0 of, okay, well, this is going to be n choose 0 x to the n plus n choose 1 x to the n minus 1 times h plus n choose 2, not going to overdo, n choose 2 x to the n minus 2 h squared, okay, and so on. Okay, I'm going to, for space here, I'm going to tighten this up a bit. So my last term would be n choose n, h to the n, and finally I have a minus x to the n at the end of that row. And that's all divided by h. Okay, so this seems like a huge mess. Okay, but some helpful things here. Okay, n choose 0. Okay, if you, again, talk to someone who took data, or run an expression through your calculator, like what's 2 choose 0 or 4 choose 0. If you run it through the definition, okay, you'll find this equal to 1. Okay, so like what usually happens, right? My xn here cancels off with the x to the n at the other side. Okay, great. Okay, what happens to all the terms in the middle? Okay, well, each of those have at least one power of h, right? My first term has an h to the 1. My second term has an h squared, all the way up to my last term, which has h to the power of n. So for each of the remaining terms, I can cancel out one power of h. Okay, so I get my limit as h goes to 0. Okay, my first term becomes n choose 1, x to the n minus 1, because the h's cancel out completely. Okay. For my second term, the power just reduces by 1. All the way up to the last one, the power reduces by 1. Okay, so the rest of my terms are going to look like n choose 2, x to the n minus 2 times h plus, okay, and so on, up to n choose n, h to the power of n minus 1. Okay, now I can substitute in my 0 for h. Okay, what's going to happen? Well, the first term, okay, nothing will happen because I don't have an h anymore. Okay, but every single thing I have left has an h, right? So when I substitute into 0, this one's going to disappear, all those ones in the middle, everything else is going to disappear because I can multiply by 0 in every other expression. Okay, so this is equal to n choose 1, x to the n minus 1. Okay, so finally, what's n choose 1? Again, talk to somebody in data. It's going to be n, okay, and that completes the proof. Okay, so I got down to n times x to the n minus 1. Okay, binomial, sorry, not binomial here. Okay, the proof of this rule, okay, will definitely be on the test and or the exam. Okay, if you don't see it on the test, you'll see it on the exam, or vice versa. Okay, but you will need to know how to prove this. Okay, doesn't matter to me which proof you memorize. Okay, if you like the first one better, use it. If you like this one better, use this one. Okay, but you do need to know the proof. Okay, the last one we're going to do is the product rule. Okay, so that funny one that we learned about yesterday. So here we go. Okay, so the limit of this, okay, the substitution part still works the same. So the limit as h goes to 0 of, right, replace with x plus h in the first part, and replace with x in the second part. And that's all over h. There's not a lot I can do here, right? I don't have a function to substitute into. So here's, okay, again, I don't want to call it a trick, okay, but this is what we're going to do to deal with it. We're going to actually add and subtract a new term that will allow me to do some rearranging here. So again, we do need to know this proof, so it's important that you learn what's the step and what's happening here. Okay, so the term I'm going to introduce in the middle here, okay, I'm going to keep my x plus h, and g of x plus h. Okay, so what I'm going to put in the middle here is I'm going to subtract f of x plus h times g of x and add it at the same time. Okay. Minus f of x g of x. Okay, apologize, I kind of ran out of room there. Or h. Okay, now we're going to make use of our limit laws and split this apart at the middle. Okay, so I can call this the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x plus h, g of x, over h, plus limit as h goes to 0 of the second half. So f of x plus h, g of x, minus f of x, g of x, over h. Okay, the reason I did this, okay, if you look at both terms, I can actually factor the numerator a little bit. Okay, they have some common terms, and again, I can use my limit laws to separate the pieces apart. Okay, so in the first half, the numerator has a common factor of f of x plus h. So I'm going to factor that out. Limit h goes to 0 of f of x plus h times the limit of h goes to 0 of g of x plus h minus g of x. Okay, hopefully you're having a bit of an aha moment here as we finish this up. Limit as h goes to 0 of My common factor in the second side is g of x times the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, so let's go through each of these limits. Okay, the first one, the limit as I go for f of x. Okay, I don't have any trouble there, so I can just sub in, right? H for 0 right there. So my first part is f of x. Okay, the second part, well, if we look at that, that is the definition of the derivative of g. So I get g prime of x. Okay, when I look at the second half, well, then as h goes to 0, h isn't even involved there. So I get g of x. Okay, and last but not least, I see the definition of the derivative of f. So this gives me f prime of x. Okay, they're in the opposite order from the rule. I'll just move them around. Okay, so if I rearrange the terms, we get the rule that we learned yesterday. Okay, proven. So that's why the product rule turns out that way. Okay, so that's the proof of those rules. Okay, again, those, especially the second two, right? The power rule and the product rule. You need to know the proofs. Okay, we can ask you those on a test or the exam. Okay, so the other rules. Okay, you've seen some of the stuff. Okay, it shouldn't be too much of a stretch to do some of the other rules as well. Okay, so here's some practice in that regard. Okay, so have some fun with that, and we will see you on Monday.